Welcome back to my YouTube channel, and in this lecture we will see the frequency acquisition in type 1 PLL, and we will see the maximum frequency range of frequency error to which we can look the PLL. Okay, so the maximum frequency error range is equal to K less than equal to K, where the K equal to KPD dot KVC, and this delta omega 0 is your frequency error. Okay, so now how this is coming, that we will see. We will try to derive this. Okay, so let's start it. So for example, this at input at the PD we are giving V in, and output we are getting V out. So let's consider V in is equal to sine omega in t, and V out equal to cos omega out t. So what will be V error? V error will be equal to V in into V out, because V error is the multiplication of V in and the V out. So after multiplication, the result is like this: half sine omega in plus omega out t plus sine omega in minus omega out t. Okay, so now let's consider at t equal to 0, omega in equal to omega, and omega out equal to omega free plus kvco dot vc. Okay, and the vc equal to 0 at t equal to 0, so omega out equal to omega free, and omega free is not equal to omega. Since you can see that omega in is not equal to omega out, okay, so there is a frequency error, and that frequency error we can denote by this, that is omega in minus omega free minus kvco vc. Okay, just we are removing omega out from this. So okay, yeah, this is frequency error. Let's convert this frequency error into phase error. So the phase error will be equal to integration of frequency error. Okay, so what is the frequency error? Frequency error, the constant term we can keep like this: omega in, omega free, and then dt minus integration kvco dot vc dt. So this will be integration of this is what, this is your omega in, you can put omega, and this is omega free. Okay, and dt minus kvco dot vc dt. Remove this is at time t. Okay, so this is at t equal to 0, the frequency error, so it will be minus kvco vc dt. Okay, or we can say, because it is constant, we are keeping it outside, and it will become t and minus kvco dot vc dt integration. Okay, so this is the phase error, right? So now we got the phase error. If we are differentiating this equation, this equation we want to differentiate. Okay, after differentiation, d phi error dt is equal to del omega 0. There was a t, so when you will differentiate, that will be become 1. So this is frequency error at t equal to 0 and minus kvco dot vc. So this is one equation. Okay, now what is the condition for PLL locking condition? The locking condition is the differentiation of phase error should be equal to 0. So right, therefore we can say right, or we can say that del omega 0, oh sorry, Okay, let's first put the value of VC. We know that VC equal to KPD dot sine phi error, right? We know this. So let's put this equation in equation 2. So the del omega 0 minus KVCO dot KPD dot sine phi error equal to 0. Now this total, consider it as K. Okay, so we can say del omega 0 minus K sine phi error equal to 0, right? Or we can say del omega 0 by K minus sine phi error equal to 0, right? So if we want to plot it, how it will look like? So this whole equation is what? This is nothing but phi error, differentiation of phi error divided by K. So let's write here phi error differentiation by K. And this is what? This is phi error, right? So now if we are drawing this only, so it will be like this, right? Now we have to add this term also, so it will be shifted by that much amount, del omega 0 by K. So how it will look like now? It will look like this, and same here, and so on. Yes. So now you can see here that there are 2 points that is considered it as K1 and this is K2. These two are the points which are the solution for this equation, right? So this is also, so you can say that in every 2 pi period there are 2 solution points for this above equation. Okay, so what we can say, phi error won't be more than 2 pi to get the solution, right? In 2 pi only, in period of the 2 pi, you are getting 2 solution points. Okay, so now the questions come, which is the stable point? Is this K1 or K2? Okay, I'm removing this left side stuff. Yes, so what we want to see, we want to check which one is the stable point. Is it K1 or K2? Okay, let me draw this again. Okay, no, remove this. Somewhat like this. Mm, yes. So now see, at K1 point, if I'm at K1 point, okay, and I'm increasing this del phi error. Okay, so if I'm increasing phi error, what will happen? You can see that the slope of phi error will also reduce. Okay, if I'm increasing phi error, then it is implying that slope will be negative. What this implies? It implies that phi error will reduce and will come back to its previous state. It means that it will go back like this. Okay, and now if we are decreasing this, what will happen? You can see that slope is increasing. Okay, so it will increase and go back to its previous location like this. Okay, so it is a stable point, right? So what we understood, that K1 is stable point. Now let's see the second point. This is K2. If we are increasing this, we are going like this, but we are seeing that slope is increasing, so it will increase only. Okay, it won't come back at this K2 position, right? And if I am decreasing it like in this direction, what we are seeing that this slope is also reducing, so it will go in this direction only. It won't come back at K2 point. So what we are seeing that K2 is unstable point, right? So what is our solution point? That is K1. Okay, I hope it is clear. Now let's see if we are considering that our point, we are at this point. Okay, now where the PLL will be able to go. So the PLL, where if it is increasing in this direction, then it will go up to here, and at this point it will be low. Okay, right. If I start from this point, I'm again repeating. Okay, then it will track all this green path, and at point this A point, PLL will lock. But still you can see here phi error didn't increase more than 2 pi, right? So see, here to here, it didn't increase more than 2 pi, right? So that is one. It is a note that phi error didn't increase more than 2 pi. Okay, so that is the condition which we saw in frequency acquisition, right? So what we call it? We call it lock-in range. Okay, for pull-in range, it will exceed 2 pi, and for lock-in range, it will be less than 2 pi. So this is lock-in range. It is locking, able to lock uh, without exceeding phase error more than 2 pi. Okay, so now let me rub it again. Hmm. So the equation was by k equal to, right? Now del omega 0 will be equal to k sine phi error. So what will be the limit? Sine phi error will be 1 or minus 1. That will be the limit. Okay, so what we can say that del omega 0 will be greater than, okay, yeah. So what is the limit? Limit is del omega 0 should be less than equal to k. So this is the maximum frequency range up to which we can lock the PLL, right? Oh, what I wrote. This. This is the equation which we have to derive. And you can see this is the derivation, right? So this is the maximum frequency range up to which we can lock the PLL. What is K? K is KPD dot KVCO. Okay, if your frequency error del omega 0 is greater than KPD dot KVCO, which is equal to K only, then your PLL won't lock. Okay, it won't be able to lock if this is the condition. So this del omega 0 must be less than KPD dot KVCO. Okay, if this is the condition, then what PLL is doing, that we will see next lecture. Okay, so I hope it is clear to all of you. Thanks for watching this video. If you like the video, please like it and share it with your friends. Thanks. Bye. Let's meet in next lecture.